All right, my name is Sergio Ammirata. I'm the CTO of DVEO. I'll be going in depth today in RIST PSK. So, hold on. Adjust my screen size here for a second. Okay, so our topic for today is RIST and pre-shared key encryption. Securing your stream, of course, is a prime concern for anyone who wishes to protect their own intellectual property, on a stream. RIST provides two methods, like Zero said, of strong encryption that adhere to AES, Advanced Encryption Standard, and we'll briefly review the first method, DTLS, before going deeply onto PSK. We will also discuss how to implement PSK with RIST, and then discuss scenarios where PSK may be a better or the only choice for the transmission. Okay, let's start with the main profile. The main profile specifies that to use either type of encryption, we need to set up a GRE tunnel. I won't presume that everyone knows what GRE stands for. It's an acronym for Generic Routing Encapsulation. It's a basic and time-honored standard developed by Cisco that enables us to encapsulate various protocols inside virtual point-to-point links over an internet protocol network. Now, it's your responsibility to set up the tunnel, but we should know that there's a lot of tips on the internet as well as libraries and applications that help you do so if you're implementing the protocol. One of the advantages of having the tunnel, it makes it easier for a RIST receiver with a NATed address to connect with a RIST sender, which is a common case on a one-to-many scenario. The other big benefit of the tunnel is that it only needs one socket once you've set up the tunnel. Just a second. All right. So let's go briefly. I'll go over DTLS briefly so that we can understand the differences. We need to look at DTLS first. To provide a quick definition of DTLS, it's essentially TLS for UDP datagrams. We can look at it as a building block. It can provide support for authorization and encryption. And then after that is done, you use RIST, simple profile, to take care of the rest and transmit your packet and perform the packet recovery. DTLS process. One of the more confusing things when you're setting up a tunnel with RIST is that which is the client and which is the server depends upon which side is starting the connection. So it becomes a little bit confusing because it's sender of the data, receiver of the data, and then it could be opposite as far as the tunnel is concerned based on who initiated the connection. In general, one side has a private address and the other side has a public address. So it may be easier to start the tunnel from the private address, and then the firewall may see that as an established connection, and that simplifies a lot of setups. So the tunnel and the sender receiver are not necessarily matching. As far as AES security, we have 256 bits and 128, but it's we should note that 256 bits will take 40% more CPU power to achieve, and there's a lot of controversy among ourselves, but some of us think that 128-bit is enough for most applications. So it's up to you to decide which one to use. Okay. DTLS, here, DTLS process. Okay, I'm on this one. You may think that of DTLS as HTTPS, like Zero mentioned, for UDP. It's the same process. You have the tunnel uses, to set up a tunnel, you use SSL certificates. The certificate can be self-generated or it can be a certificate authority generated. You can have certificates with or without validation. It's up to the implementer to decide how that handshake is going to happen. The concept at the end is that though there are maybe a few moving parts, it's a way of verifying that each side is who they say they are. It's a way to authenticate both ends before starting the data and the encryption through the tunnel. The bottom line is that once you've got the tunnel established, it operates much like RIST simple profile inside. So let's review the authorization with a diagram, okay? In this diagram, we're still talking about DTLS. We see a somewhat simplified overview of the communication that will pass between the server and the client. What the center panel illustrates is that it requires a few round trips to set up the tunnel with the DTLS, and then which becomes one or many simple profiles that can go through it. On the bottom, on the notes, we see notes that explains that in order to verify the certificates, we need a real-time clock, just like with an HTTPS and a computer. In this case, we're also showing a client-initiated connection, so it will be a reverse NAT, so that the firewall in front of the client will see it as an established connection and data will flow through. So this is the basics of what happens during DTLS. So now that we have that perspective, let's move to PSK. Okay? We can see PSK shares a number of things in common with the TLS. It also has AES encryption and multiplexing on it. Then we see there are two major differences as well. One, it does not have an authentication step. And two, it supports and requires key rotation. When we look at the GRE header here, we see that it now includes two new elements that are mandatory when you do PSK, a sequence number and the key/nonce. In the normal literature for GRE, they typically call that field key. We've labeled it here with a slash because we use it as something else called the nonce. So keep that in mind. Okay, PSK. We assume that the receiving side and the transmitting side have already shared a common passphrase. We also assume that this sharing has been done through some non-RIST form of communication. Once the tunnel is established, all the packets that pass through will have AES encrypted payloads. Okay? Now, using the contents of the sequence number field that comes in the GRE as the initial vector, we can decrypt the payload with an AES key that is derived from that key field that I just mentioned, plus the passphrase and an industry standard protocol that lets you do that calculation. Key rotation takes place whenever the nonce field is changed. So this nonce field must be changed at least every time the sequence number wraps to 0 to maintain security in the protocol. However, the sender can change that as often as they like for whatever reason. Maybe for marketing reason, they say, we rotate our keys every 100 milliseconds. They can do that. It's up to the implementer, but at the very least, every time the sequence number goes back to 0, they must change that nonce. Okay, so let's summarize again, step by step, what's needed to use PSK. Step 1, the passphrase is pre-shared outside the tunnel through some other method. A phone call, an encrypted end-to-end instant message, your choice. However you want, or you create a sophisticated protocol using a website, a login, however you want it, you get the key to both ends. Not the key, the passphrase, some secret code that they both exchange. Step 2, the tunnel is established by the simple fact of one side opening the UDP connection to the other. There is no authentication, there is no fancy handshake. The minute one side or the other sends the first packet, that's it. The tunnel is established. That's step 2. Step 3, the sender sends the sequence and the nonce in the header to the other side. Step 4, the receiver decrypts using a key derived from the pre-shared passphrase plus the nonce, like we mentioned. Step 5, at sequence rollover, whenever that happens, 2.1 billion packets later, or at an arbitrary point if you have that requirement. The sender sends a new nonce, and then the step 6, the receiver has to regenerate the key at that point to continue decrypting. Okay, so here's the equivalent diagram that we showed for DTLS. Now, this is what happens with PSK. The diagram shows the communication within an already established tunnel for PSK. Since there is no handshake, the tunnel connection really is initiated by any data packet on either side. For example, the client hello message or the server hello messages could be the initiators of the tunnel. You don't have to send a special packet. You can just start a simple RIST simple profile, and suddenly, boom, your tunnel is open. And that tunnel is going to remain open because on the simple profile, those messages, the hello messages, they travel back and forth all the time. So even when the client initiates the connection, the tunnel will remain open. There's no need for a keep alive in that case. And I think we made that optional, the keep alive message anyway. Right. So we call that the keep alive. So the other difference versus the DTLS diagram is that the server doesn't have to listen to any ports unless a reverse NAT connection is required. In other words, when the server is sending out encrypted RTP and RTCP packets, it assumes the receiver can decrypt them because it has the pre-shared passphrase. So it doesn't need to have any feedback from the other side to decrypt that data. So why and when to use PSK? The difference between the protocols will give us an idea when we should use PSK as opposed to DTLS. First, when the receiver or the sender doesn't have a real-time clock. This is not as infrequent a condition as you may think. The Raspberry Pi, for example, which with the 20 million units sold so far, has no real-time clock on its circuitry. So you couldn't implement DTLS on it unless you disable pretty much everything that's good about the SSL authentication, which is validation of the times on the certificates. Secondly, another use is when you have one sender, too many receivers. And third, in a special network situations, such as when communication must be one-way only, maybe a satellite link, or an asymmetric or disjointed network, where you have path going in one direction on one physical network, and the return has nothing to do with it. It's a separate layer 2 protocol with separate routing. You can achieve full two-way communication on disjointed networks, and you cannot do that with DTLS. So getting the best out of PSK. In the one-to-many scenario we just mentioned, because RIST also allows us to add for error correction, we might be able to use PSK as a near ideal means of protecting a one-to-many distribution. Basically, by adding FEC with a small overhead, we can reduce the re-request for any drop packets which would be coming from many receivers in the one-to-many scenario. So, think about a small hotel or, that type of scenario. You don't need to use unicast necessarily. You can use a combination of this. We would no doubt require some tuning on a stream-by-stream basis, but it might be possible to write at a highly efficient means of large group distribution for RIST streams. In this manner, either unicast or multicast and encrypted streams. As to the one-way network scenario, this only works when the sender initiates a tunnel, of course, because there's no return channel, and it only makes sense to do it if you also pair it with FEC, mandatory FEC to some extent, because there's really no way of receivers to tell you or reach the sender for any retransmissions. For in a one-way scenario, the optimal use, again, is sender initiates a connection to a multicast or unicast if there's proper routing all the way to the end, and FEC is turned on. Okay, this is just for informational purposes. This is how the header looks like with the FEC. And, you know, this is what the diagram would look like. So this diagram is showing the communication through the tunnel for a one-way network scenario. Assuming the server is setting up the tunnel, that's why let's assume that server hello message automatically sets up the tunnel, and the client automatically detects it and starts receiving data. It assumes the player would need to assumes that the player would have an address that the sender can reach. Is a one-way disjointed network, but there has to be some sort of IP communication so that the server can send to a multicast IP or to a unicast IP, and somewhere in the other side of the planet, there's a machine listening to that IP in a one-way UDP socket type of way. Or it could be perhaps a VPN address, a one-way VPN address or some security model that requires one-way communication. It's not necessarily satellite. And as always, the player, client player, and the media server, or whichever two pairs you have there, they must have shared the passphrase some other way. So in summary, DTLS and PSK both provide AES encryption support. They both require tunneling and can aid the setup of a connection where one side is NATed, so one public, one private. PSK supports and requires key rotation. DTLS, in theory, supports also key rotation, but we don't have any particular implementation or where to explain it. So as of right now, unless somebody comes with a white paper, we only have key rotation using PSK. And only PSK can provide the flexibility for some additional scenarios, like two of the ones I just mentioned, one-to-many, including multicast, and one-way or disjointed networks, over satellite or wherever it is. Thank you. Right. I myself envision this as a set-top box protocol. Whether it's in a local hospital, in a bar, small deployments of a few hundred units, it's a no-brainer. You can secure your content, have acknowledgments that will not kill your network. You put some safety mechanisms. In those scenarios, I think it's easy to implement there. More difficult scenarios, which could also be studied and could have success, are straight. When you control a client, you can create an internet-based distribution media server that pushes to each customer at the end unit if you control the player using the RIST protocol. Open it up. If you think about it, this is not new, the fact that we want to send UDP to the customer. It is the best experience as far as bandwidth saturation or leveraging the maximum on your bandwidth. UDP transmission will do that, and we used to think this was the way to go years ago, 10 years ago, when RTP was hot. Let's do RTSP over the internet. And the cameras, let's do RTSP, that's the best thing, it's sliced bread. It will negotiate, we'll tell the camera or whatever server to send us a UDP stream. Eventually, we stopped doing that because UDP streams are lossy. This now gives us back the best of both worlds. We can build on top of the protocol with additional features and reach that as well. And then the third one, which is important, is we can leverage this as a way to encrypt satellite communications again. Satellite communications, they do typically have a FEC at the RF level. And now we can put as much FEC as we want inside the data stream and encrypt it at the same time. Some people say that PSK is insecure. Okay. Well, I say that the way we implement, yes, there are ways to implement PSK that are very insecure and hackable, etc. The way we've implemented PSK here is not. It complies with the NIST standards, with all the possible published papers about how to use PSK securely. And the main key for us was the ability to have a sequence number that's unique throughout the lifetime of the stream. Without that, and without using that as an initialization vector, yes, it would be considered insecure.
For PSK, you mentioned the two number of base supported key, 128 and 56. I wonder whether it's necessary to go to 256 base for the key length. To add perspective, in the DRM world, the whole industry seems to be happy with the 128 base. That's to any user. RIST is used in a more controlled, slightly more controlled environment. Why do we need to go so high?
Well, because we need to accommodate the needs of all possible users of RIST. Some of them are heavy into the military government connections, and they use nothing but 256 and think 128 is for kids. You know, others, you know, like my company, most of our customers are happy with 128-bit, have never complained about 128-bit not being good enough, and it saves 40% CPU. So, you know,
Is there any comparison as in terms of the cost, cost in the latency and cost in CPU or between 128 and 256?
there are many studies that are published online, and that one of them is where I got this number 40%. They show that it takes 40% more CPU usage on the same machine just to do the exact same transfer with 256.